So we're going to continue working on chapter 14. I thought we could finish this today. We're going to be a few slides short of that. So because of that, I'm going to move back to mastering chemistry today. So it was due tomorrow, but I'm going to move it back to Wednesday. The way we can cover those last topics of class, which would just be catalyst. You can still do 90% of the problem based on what we covered today. So again, that's a lengthy problem set. If you haven't started it yet, you better get to playing with that one because it eats some time up without a doubt. So the last thing we talked about on class last Wednesday was how to determine reaction order experimentally. So we're going to do a few things with that using, it's called the initial rate method, where you change the concentration of one reactant and you look at how the reaction rate changes, or the initial rate changes with response to that reactant. So that's kind of where we stopped on Wednesday. So set by whoever you want to set, because we're fixing to do some questions on that. Yes?
That's a question. So on that problem right there, when you're comparing the what changes, like 2 times, same 2 times. So how do you know, I'm just saying like in general, how do you know that that is a first order, a zero order, first order, second order?
Okay, so we'll do go overview this last problem that we did just quickly to compare the first set. So if you look at experiment 1 and 2, the concentration of this reactant doubled, this one stays the same. Okay, so you look at the change of the concentration of the one that went up, and then you compare the rate. So the concentration doubled and the rate doubled. So the rate got twice as large. That means it's a first order. Okay, so we know that with respect to this one, that this was a 1. That told us it was first order. Now you look at experiments 2 and 3. So the reactant 1, the tetracyanate, it stayed the same, but what happened is 3 is half as much as in 2. So if I look going from 3 to 2, it doubled in that way. So twice the concentration, but if I look at the rate, it was 2.27 versus 9.08. It's 4 times as much. So double concentration, 4 times the rate, that tells me it's second order with respect to this one. So that tells me this number's 2.
So it doesn't matter which way it is. So if it decreases or increases, as long as there's a change in between, like the second and third, or the first and the third, as long as it multiplies.
Well, I mean, if it's zero order, it won't change. So that's absolutely possible. So I told you the scenarios that you need to be able to diagnose or describe are zero order, first order, second. So that's the possibilities that we'll look at. It doesn't have to be, as long as you change the concentration, it doesn't matter what the factor is, as long as you can know what the factor is, you can compare it to the factor for the rate change. So you can change the concentration by a factor of 10, and look at the change in rate. So as long as you know how to compare this number to this number, you can determine the order. Okay? Anything else? All right. So here's your first one, and I'll let y'all talk to each other on these, but you got a time window. So I'm going to give you a couple minutes to figure this out. So I want to know what's the reaction order with respect to the hydroxide. So the only thing I'm interested in is with respect to the hydroxide. So figure out what the order is with respect to the hydroxide in the system. Again, this is a group problem. You can talk to each other. First thing you got to figure out is which pair of reactions to use. the answer in? Oh. Okay. Not many talking about it, your time's fixing to expire.
Because the wage, because of that fee, interest rate goes up by 3. Because it does affect the initial rate. You're saying the initial rate.
Okay, so like on the previous page, I'm just going to go back just a second to answer his question. So on the previous example, you can write the rate equation. It's respect to one of the reactants. So on this one, it would be with respect to the OH if you wrote out the rate equation. So what's the order with respect to the OH? All right, I need one more answer. Okay, so everybody went with choice B, so we either all got it right or we all bombed it. They all got it right. Okay, so how could you quickly answer that? Okay, we're looking at the two where the oxide or the hydroxide ion changes in concentration. So we would compare these two. I'd call them 1 and 2. These two stay the same. So this is the one where it's different. Now look at the rate. So the concentration goes up by a factor of 3. And if I look at the rate goes up by a factor of 3. They go up by the same amount. That tells me that's first order. That should be able to answer it that quick. Okay, question on that? Because now you got a follow-up question with the same data. Okay. Question? All right. Now I want you to tell me the value of K, the rate constant for this reaction. So I give you the reaction, the rate, and I'm looking for what is the value of K. What are you going to have to do to answer that? Again, this will be a group problem too. We talked about how to calculate K. We've already done examples of that on Wednesday. And I'll give you a hint. From the previous problem, we determined this was 1. Oh, wait, never mind.
Yes, the order. By the rate, the initial. That's you just have to. So
Yes, if I can trust my fact.
So I look at the first line.
Yeah, so it'd be the second, so you do by two.
Yeah, so I got
Rate.
CO2 cleared.
So you're doing the first box. First column.
Yeah, I guess.
So go with the rate.
So is that what you're using?
Yeah.
Yeah, this is.
And do you actually? Yes.
You have to square this 6 out and divide the rate number by both of those numbers. Divide
What do you mean? What is it? Oh, you mean the
248.
Okay, maybe getting close.
I think so.
Yeah, that's what I'm at now.
What'd you come up with?
Oh, that's all right. Yeah, that's what you got. You just use the first box. You just use
Right.
just rearrange.
Okay. 10 seconds. Need one more answer. Okay, you're all in. Everybody voted, right? Okay, let's see how we varied. So almost everybody liked choice D. I'm not sure if we clearly understand how we chose choice D, so I'm going to work it real quick. Okay, so the first thing you need to do is find out what X is. So for the next one, this pair stays the same, so I'd want to compare these two. So the concentration between 2 and 3, or between 1 and 2, it's 3 times higher in 1 than it is in 2. And if I compare the rates, the rate is 9 times bigger in 1 than it is in 2. So that tells me if I triple the concentration, I get 9 times the rate. 3 squared is 9. That tells me that this is a second order. Okay, so now I know what the values of X and Y are. So the orders with respect to each reactant, I can take and solve for K. K is equal to the rate divided by the concentration of reactant raised to the powers. And it wouldn't matter which line I chose to do. I'm just going to do line 1 because that's the one on top. But it would work for any of the data. Put in the concentration of the first reactant. Remember to square it. The concentration of the second reactant. And when I do, then D is D. It's 230. Okay, so we'll do this exact process in lab this week. So we're going to run data, collect rate information, and do a lot of replicates of it. And we're going to, instead of just calculating this once, we're going to take 6 trials of it and average it together. So we'll determine the order in the first sets of the experiment. And then once we know the order, we can take the rates that we've determined for all 6 trials, average them together. Should have a good representation of what the rate is at room temperature. Okay? Any questions on this? So this is a guaranteed test question. So I can say yes.
So the overall order would be 3.
It'd be third order overall. Yep. But when we describe kinetics, typically we're describing kinetics with respect to a particular reactant. So even though we'll talk about things that I told you would be responsible for doing, like the integrated rate laws, like we talked about in the earlier in the chapter for either zero, first, or second order. Those are for individual reactants. And now we're talking about complete reactions. So a little different. Okay, so the next effect we look, we talked about all of this portion of the chapter, the earlier portion, we talked about things that can change the rate of reaction. This was the effect of concentration that we've been talking about, what we spent most of Wednesday talking about. Now we want to look at the effect of temperature. So when we look at the rate constant K that's in our rate law, that K value is temperature dependent. And the rate relationship to temperature is called the Arrhenius equation. It says that the rate constant is equal to a frequency factor, capital A, and then E raised to the power of the negative of the activation energy divided by RT. Talk about what each one of those terms are. Temperature is the temperature in Kelvin. R is the gas constant, 8.314. Now we've got to be aware of its units. So it's in joules per mole, degree Kelvin. So that means the temperature has to be in Kelvin. And usually when we describe activation energy, it's in kilojoules per mole. So we have to switch joules to mole to kilojoules per mole to usually come up with the final answer, the answer that we need. And this A, this frequency factor, is related to the energy as it approaches the activation energy. And this E sub A is the term called activation energy. It's the minimum energy required to get the reaction started. We'll talk about that just a little bit. All right, so if we look at the reaction between hydrogen and oxygen and oxygen will react very violently with one another to form water. Okay, put hydrogen and oxygen in a balloon, touch it with a candle, it will explode, loud boom, produces water in the reaction. However, it takes something to start that reaction. If I just put hydrogen and oxygen in the gaseous form in a balloon, I can fill it up, tie a knot in it, nothing happens. What it requires is this bump of energy to get it started. It's called the activation energy. Okay, so it could pick it up from the environment and slowly that reaction could start happening. Or most often it needs something to promote or start the reaction, and that allows the reaction to occur. So we would get it by touching a candle to it to get the initial burst of energy that you need. Once the reaction starts, the fact is this an endothermic or exothermic reaction? How would you know that? Gives off heat. How did you know that? Because it's a flame, right? But looking at this energy diagram, how do you know it's exothermic? It goes down. So you start with the reactant energy here, you end up down here. This amount is the amount of exothermic energy it's lost off. Okay, so once it gives energy off, this energy can go back into the next reactants and give that barrier. So it's one of the things, once it starts, then it's downhill. Okay, because it's got excess energy coming from this reaction that just happened. But it needs this energy to overcome this barrier, and this barrier is called the activation energy. Now, whenever a reaction occurs, we describe this energy barrier in terms of the amount of energy needed to convert the reaction or reactants into the activated complex. We also call this the transition state. So the activated complex is a species of chemical that's kind of an intermediate between the products and the reactants. It's where you've partially broken some bonds and you form some new bonds in the system. And it's always a very high energy state because you've got these partial bonds that are formed in the system. So this is the isomerization of methyl isonitrile. So what happens in this is you make this compound and you make the CH3 called a methyl group. It's attached to the nitrogen. But if you apply enough heat to it, it will spontaneously spin around and the carbon will be attached to the CH3 group. So it'll do an inversion on the right-hand side. So it goes from this state, where the blue represents the nitrogen, to where now the nitrogen is a terminal. So it's a rearrangement type reaction. So for this to occur, what happens is this has to start, instead of being in line like it is now, so that would be looking at the geometry. So now I've got to think back to the stuff that I learned in at the end of chapters 9 and 10. So looking at that, what type of electron geometry is this? This is an AB who? Okay, how many things are attached to the central atom? Just 2 things. Remember, it doesn't matter if they're single bonds, double bonds. It's how many things are there. No lone pairs. So AB2 is a linear. So this is a straight line through this thing. Okay, so for it to start to break this bond, this straight line's got to bend. Okay, and it's got to start tilting up out of where it wants to be. This bond starts to weaken as it's stretching out. This one starts to come around because it's going to start forming a bond between these atoms. This is called a transition state, where it's going through this intermediate. It's breaking one bond, it's forming a new bond simultaneously. So it's going to have to actually reach a point that's going to be the high energy point, what we call this this activated complex, where it's going to have to go up in this non-traditional position. It's going to have to go up a full 90 degrees from where it should be, and that's the highest energy state. The energy that it takes to get to there is the energy barrier, or the activation energy. Once it gets to that, then it can flip on around, and the nitrogen come on the end, this carbon could fall on down, and then it's releasing energy at that point to form the product that it needs. The activated complex is the one that has the partial bonds associated with it as it's undergoing this rotation. The book talks quite a bit about this activated complex, and we talk about it more in some advanced classes. We definitely talk about it in terms like computational chemistry and physical chemistry. In freshman chem, we're just trying to understand the basics of kinetics. I'm not going to go into it a huge amount, but when we talk about the catalyst at the end of the chapter, the catalyst plays its role by helping this activated complex form. Okay, so it does something to the chemical system that helps it get into this state easier. So it could be something, if you want to think of it, if you wanted to help that along, if we could touch the microscopic world of a chemical reaction, we'd want to grab a set of tweezers and twist that so it's at a 90-degree angle. That would help that reaction occur. In its own way, that's what a catalyst does. Okay, it takes something that's at a normal state that's stable and adjusts it to a non-stable state to help promote a chemical reaction. And we'll talk about those when we get to catalysts in just a moment. Now, the frequency factor, well, actually, it'll probably be tomorrow or Wednesday. The frequency factor is that A term. What it represents is the number of molecules that are beginning to form this activated complex in a given period of time. So as the frequency factor approaches 1, that means that 100% of the molecules could reach in that point where they have enough energy that they could form this bond in a system. So the frequency factor has values between 0 and 1. None of the molecules have enough energy to do it, or 100% of the molecules. 1 would be all of being there. And if we think about that fraction, the higher the energy that it takes, the fewer the molecules are going to have enough energy to overcome it. So that's where the temperature dependency plays a role. If we increase the temperature of the system, we increase the temperature of the molecules in that system, more of the molecules have enough energy to overcome the energy barrier. That's the reason if we increase temperature, we increase the rate of a reaction. Right? And if you remember, I gave you something called the chemist rule of thumb we talked about. That was that relationship at the start of the chapter. This kind of shows the why of what's going on. We talked about what's happening with energy as a function of temperature, and we talked about like motion, like kinetic energy, when we talked about gases way back in chapter 4. At a given temperature, at a lower temperature, you have this distribution of kinetic energies. At a higher temperature, that distribution shifts further up. So if we look at the activation energy, if this activation energy is the minimum energy required, at the lower temperature that's in the blue, so I'll highlight that in the blue, only this small fraction of the molecules has enough energy to be activated. All right. But if we looked at the higher temperature system, in the higher temperature, that fraction jumps all the way up to here. Maybe it's a third of the molecules where it was 10% at a different temperature. And as I keep increasing the temperature in the system, so if I would go to yet a higher temperature in the system, I could push almost all the molecules into that form. So if I went to a temperature 3 up here that was way up here, I could get the distribution like this. I could get practically everything in a state where it could readily react. That's the temperature dependence on chemical reactions. It makes some reactions occur at room temperatures would be molasses slow, but if I heat them up just a little bit, I can really get them to occur much, much quicker. Okay, so apply that chemist's rule of thumb. Think back what that was, what I told you. Put in the notes if you need to. But use that to answer this question. The rate's 100 molars per second at 20 degrees. What would it be at 40 degrees? So it was a pretty simple rule. All right, one more. Okay, everybody's voted. All right, so predominantly we had two, well, not predominantly, we did have two answers, B and C. So B says 200 molar per second, C says 400 molar per second. Okay, how would we approach this? All right, so the rule of thumb that says for every 10 degrees Celsius yields twice the rate. That's the chemist's rule of thumb. Every time you change the temperature 10 degrees, the rate approximately doubles. So we're going from 20 degrees, go up 10 to 30 degrees. So the initial rate was 100 molar per second. That means in this first step, it would go to 200 molar per second. Then we go from 30 degrees to 40 degrees. Okay, we double it again. We would double the rate, 400 molar per second. Answer C. Okay, that's how we use the chemist's rule of thumb to determine what's the influence of temperature just roughly on a system. Okay. Now we're going to learn how to use the Arrhenius equation to do this in a much more quantitative way so we can know exactly how it would change per degree. So question on that. That's a probable test question too. Okay. You start looking at the old tests, you're going to see some stuff like that. All right, so this Arrhenius equation, if I take and plot the rate of a reaction versus the temperature of the reaction, I find that it's not a linear relationship. Instead, what I see is that it bends up in an exponential relationship. And we can explain that because if I look at the Arrhenius equation, the rate is proportional to the temperature raised to the E power. Okay, so it's E to the X. K is, I got to write that. I can't do that with highlighter. All right, K is proportional to E raised to the temperature, power of the temperature in Kelvin. Okay, so remember the little fish sign means proportional. You raise it, it's direct, has a direct relationship. So it's proportional to that exponential power. to make it a linear relationship, what I have to do is take and convert it to something that would make this linear, and I do that by taking the negative or the natural log of K, right, and I plot that versus 1 over the temperature. And when I do that, the y-intercept becomes the natural log of the frequency factor A. So by plotting 1 over the temperature, this term becomes the slope. So the slope is equal to a negative of the activation energy divided by R. So what it becomes in a system is when I plot the natural log of K versus the inverse of the temperature in Kelvin, I can find the slope of this equation. And once I know the slope of this equation, I can rearrange it and I can easily find out what the activation energy is. Okay, because I know the value of R is known at all times, I can rearrange this by just taking the negative of R times the slope, and I've got the activation energy. This is exactly what we're going to do in 2 weeks. So this week, we're going to find out what the order is and the rate constant. The next week, we're going to do the same reaction. We're going to change the temperature. And we're going to find out what is this energy barrier required for that reaction that we're doing. Okay, so that's the things that we're going to do in lab for a little bit. All right, so here's an example of some data. I've collected some data. I'm going to know the rate versus temperature, and I plotted it so that I've got the inverse temperature on the x-axis, I got the natural log of the rate on the y-axis, and it gives me an equation y equals mx plus b. So it's a straight line, I can see that, and if I solve this equation, plug in the values for it, I can find what the values of the activation energy is. So actually I just went and took this, want to put this to play in a data set. Here's a data set that we've got. We know that the activation energy for this is the decomposition of ozone. So ozone's O3. It decomposes into O2 and a monoatomic oxygen, which is not very stable. And it's been measured at all these different temperatures. So we go from 600 degrees up to 1900 degrees. So I think that's 12 points in there. And we know the rate at each one of those. So if I take and plot that data, the natural log of K versus the inverse of the temperature in Kelvin, and get an equation for this line, Excel tells me that y is equal to this number, which represents m, times x, plus the intercept. Okay, so I want to show you how to plot that right quick, because you're probably have a mastering chemistry problem where you need to do a little of that. And I made a little bit of a video that explains this, but I just want to go ahead and show you how to do it in real time. And I haven't even plotted this. I just entered the data points a moment ago. So I'm doing it myself. First time. And I'm really hoping it comes up with the same number. All right, so this is, where's the one I just created? Right there, literally 2 minutes before I walked in. Okay, so here is, no, that's not it. Select refresh. There it is, the ozone decomposition. Here's that data where it's the rate versus the temperature. I'm going to make it a little bigger so you can see it. So the other thing, I need to set this up so that it's 1 over 10. All right, and then I need the natural log of K, the rate. All right, or the rate constant. So to come up with those values, I just take 1 divided by the value for the temperature. So it's A2. And the good thing about Excel is if I drag that function down, it repeats that calculation. So this is 1 over, if I look at this one, 1 over A3, 1 over A4, etc. And then if I wanted to do on this column, I want to make the natural log, so equals ln, parentheses, what these rate constants are. So the rate constant, close parentheses, enter, and it gives me this number. I'm going to do the same thing. I'm going to drag it down. So down here at the end, I've got the natural log of the rate constant that was in the cell B15. So to plot this out, I'm going to highlight the data that I want to plot. Escape that. Highlight the data and go to Insert, and I want to go a linear graph. until it goes scatter. All right, that looks kind of like what that other did. All right, so I could put titles on it. I'm not worried about that for this. So let's go back and look at the notes. That's kind of what the other one looked like. So that's positive there. And then I'm going to click on a data point and right click on it and tell it to add a trend line. And it starts to put some information in here for me. And I want to tell it to just display the equation for me. And when I display the equation, it shows me what this value of this equation is. So this number I'm going to highlight here, so that represents the slope of this equation. So the slope is a negative 11,202 versus what the notes have they forgot the negative. I'll say that. And how do you know, looking at this line, that's positive slope versus a negative? How do I know that that's a negative slope? It's going downhill, exactly. Positive slope goes uphill. So it's a negative 1.12 times 10 to the fourth. So we're pretty close to having exactly the same number to each other. That's how, if you had the data, you would find out what the activation energy is, and that's the exact same thing that we're going to do in the lab. We're going to do the temperature measurement at about 5 different points, and we're going to make that plot next week. So that'll be what we're going to do next week. So now that I know what that slope term is, if I want to know what the activation energy is, all I have to do is take the slope and multiply the slope by the negative value of R. So now we put our negative back in it. So there's my slope value. Multiply it by a negative of R. What I find out, the units of K, top and bottom, cancel out. And I've got joules per mole. So it's 9.31 times 10 to the fourth joules per mole. Or if I convert that to kilojoules per mole, which is the common way I describe it, I would move the decimal place over 3 times to the left. 93 kilojoules per mole.
Why do you use a negative of R?
That's the good question to ask. I'm going to go back to the equation that we had for the Arrhenius equation. Because this is a negative, we got to get rid of that.
Okay.
So the negative and negative make a positive. Right? Again, this is one of the things we're going to learn how to solve. So this is how we take experimental data in the lab. We just vary the temperature, see how the rate changes. We can learn what this activation energy is. When we discover a new chemical reaction, we're trying to classify new reactions. The standard thing we do. I want to know what's the order of that reaction. The second question I have is I want to know what's the activation energy. Then I know what type of temperature I need to run it at to have the optimum reaction. Do I need to run it warm? Does it need to be cold? Every reaction is different. You got to figure out what you need for that particular reaction. All right. So in the engineering aspect, that's the way you figure out how to make it work in the best possible way. Okay, so this is kind of like what we did in the previous chapters with the Clausius-Clapeyron equation. And actually, the equation looks very familiar to what we had. Instead of having enthalpy and vapor pressures, now we've got rates, constants, and we've got activation energies. So this is the 2-point form of the reaction. So the 2-point form of the Arrhenius equation says that the natural log ratio of K2 divided by K1 is equal to the activation energy divided by the gas constant R times the inverse of T1 less the inverse of T2, close parentheses. And if I look at this, there are basically 5 variables. So the only thing that's not a variable in it is R. I know what R is. So there's 1, 2, 3, 4, 5 variables to solve for in the system. If I know any 4, I can figure out what the 5th is. Right, so this is going to be kind of like what we did with the vapor pressure questions on the last exam. Don't kill yourself this is going to be one question on the test at the most. Don't kill yourself if the math is eating you up on this, but I'm going to work several examples. So I hope you can follow along with it easy. Okay, so key thing is you got to pair up the T's and the K's. So we've got to recognize that T2 goes with K2. And we've got to recognize that T1 goes with K1. You've got to keep those pairs straight. If you don't keep the pairs straight, you're not going to get good results out of it. All right, so here's my first example. So I've got a reaction, and that gives you the reactants. It says the rate constant is 2.57 at 701 degrees Kelvin, and it increases to 567 if I increase the temperature to 895 Kelvin, and I want to know what the activation energy is. So this activation energy is the E sub A. I'm wanting to find out what that is. So kind of the thing we have to do is we just simply have to pair up where our K's and my temperatures are. It doesn't matter which one you call 1 and 2, okay, as long as they're paired together right. All right, so I'm going to call this rate, I'm going to call it K1, and it's going to be paired with T1. I'm going to call this rate K2, and it's paired with T2. Okay, so knowing that, I'm just going to take and plug it into the equation. I've got the 2-point Arrhenius equation at the bottom of the page. It says the natural log of K2, which is 567 molar over seconds, divided by K1, which is 2.57 inverse molar over seconds. So now when we put those numbers side by side, I can realize this change in temperature, it changed almost 200 degrees, and this rate is cruising faster. It's relatively 2.5, and now it's 560. Okay, so it's almost 200 times faster occurring now. All right, so temperature makes a huge difference. E sub A is the variable I'm solving for. R is 8.314 joules per mole degree Kelvin. In my temperatures, I put the inverse of T1. All right, so T1 is 701 plus the inverse of T2, 895. All right, if you write that down correctly, that's half the points. Okay, but I'd like for you to be able to solve it. The approach that I would use to solve it is everything on the left is just a number. Okay, and then I'd take what's in the parentheses on the right and make that a number. So let's just go through those steps, see if we can rearrange this to find out what the activation energy is. All right, so I'd start with what's on the left. I would divide that out. So inside the parentheses, this is 220.6. I take the natural log of it, and I get that it's 5.396. Okay. Now the first thing I'm going to do is multiply this R value over the other side. So 8.314. All right. I'm going to keep the units of joules per mole. The K is going to cancel out with the inverse K that's in this one. So the K's are gone. Now I'm going to take what's inside this parentheses and find a numerical value for that. So 701 inverse less 895 inverse. Subtract it, and I get that it's 0.000309 with an insignificant 2. Insignificant 2. All right, so that's up here. I want to divide this to the other side. So it's basically this number here. I need to divide it to the bottom, so it's going to go down under here. So 0.000309.2. That equals the activation energy. And I get a pretty big number. $145,000 and some change joules per mole. Most commonly, I express this in kilojoules per mole. So 145,000 kilojoules per mole. Anybody else get that number? Okay. since I knew everything but this one term, right, I'm just plugging everything in I know, and then cross multiplying over to isolate that E sub A out. I didn't have to take an anti-log or anything with this one. Now it depends on the variable you're looking for. So sometimes we're going to need to know what the rate is at a new temperature, and to do that we're going to have to take an analog.
So this equation is the exact same as the Clausius spectrums part 2 or whatever?
Well, it's not quite exactly the same, but it's very close in terms of the way we set it up to solve. It's got different parameters in it. So the Clausius-Clapeyron had a negative in it for the delta H, and we always had to take the delta H and convert it from kilojoules to joules. Now we have to do the opposite of that to go from joules per mole in the end to kilojoules. So it's kind of similar. Okay. All right. Next example. Okay, I've got a first order reaction. So the reaction is methyl chloride with water to produce methanol and hydrochloric acid, HCl. Key thing I need to know is that the rate constant, so there's a lot of words in there in between, but it tells me the K at 25 degrees. So what essentially I have is this is K1 and this is T1. All right, so I know K1 and T1. I want to know what is the rate constant at 40 degrees. So this is T2 if the E sub A is given. So now I'm looking for what is K2 at this new temperature at 40 degrees Celsius. I know what K1 is, I know what T1, and I know what T2 are. I know what the activation energy in R is. So I'm looking for a different variable this time. Okay, so what do you think the first thing is I need to do to work this problem? Say again? Okay, before I start writing numbers in this equation, is there anything else I need to do to in the data? Gotta get Kelvin. And I gotta get E sub A from kilojoules per mole to joules per mole. That way it'll cancel out with R. And then I've got to get my temperatures to Kelvin. So 25 plus 273 is 298. So T1 is 298 Kelvin. And T2, 40 plus 273 is 313. 313 Kelvin. Now I've made those changes, I can plug it in and start rearranging. Okay, so let's do exactly that. So I've got the natural log of K2 divided by K1, and I know what K1 is. It's 3.32 times 10 to the minus 10th. Wow, that's a small number. All right, times the activation energy is 116 times 10 to the third joules per mole. R is 8.314 joules per mole degree Kelvin. The temperatures 1 over T1 first. So 1 over T1 is 1 over 298. That's 1 over T2, which is 1 over 313. Everything on the right-hand side is just a number. Okay, so everything over here on the right is going to equal to whatever this number is. So I'll try to do it. I'll try to do it. My approach I would do to this is figure out what's in parentheses first, then multiply by E sub A and divide by R. Okay, hopefully somebody came up with what I came up with. I got 2.243 in significant sets.
I'm very close, putting around this.
Okay, let me make sure I didn't put a digit in wrong.
2.2. I think it's just the way
And I got the same thing again. Right, so now I know that. So what that tells me is that the natural log of K2 divided by whatever K1 is, I know that value is equal to this number, 2.2437. So I want to isolate what K2 is. So I need to take the anti-log of both sides. So I'm taking E to the ratio of K2 divided by K1. And I've got to do that to both sides. 3.7. So when I do it to the right-hand side, this becomes 9.278. Eight, 9.428. Okay, and if I take the anti-log of a log, that basically cancels out. So this term is just equal to K2 divided by K1, which is the 3.32 times 10 to the minus 10. So if I want to know what K2 is, simply take this term, multiply it up here, and it tells me that K2 is going to be about 10 times larger, roughly. And our units are inverse seconds because it's first order. Go ahead.
Can you go over the math right side here? Because I'm getting like 0.02.
For which step? The first line or the
The right side.
over here?
No, on the
This side. Okay. So I took 298 inverse less 313 inverse, and I subtract those two. I get that this number is 1.608 times 10 to the minus fourth. Okay, so that's what this equals to. Okay, then I took and multiply it by 116 times 10 to the third. Nope, it's 116. Yeah. Yeah, I get the same number again. Okay, other questions? Huh? So this is kind of like if you knew this is kind of like the exam question with the Clausius-Clapeyron equation. You knew the vapor pressure at one temperature. What's the vapor pressure at the new temperature? Knowing the enthalpy of vaporization. So I had an exam question like that. If you choose to do your math a little different, that's fine. I mean, you can do all the math and rearrange this algebra with the algebra and then solve for K2 before you ever plug it on your calculator. I think it's much easier, since you know everything on the right, make that a number and calculate that. So you do the approach you've learned how to solve the math. You know, one way to approach it. Okay? I know it's coming. Okay. Yeah. All right. So I've got a rate constant at one temperature, a rate constant at a second temperature. Want to know what the activation energy is. So try to work it on your own. Armstead. Few answers. Four more. Last two. Need one more. So most abundant answer was B, but 30% of you went with something else. So let me set it up and work it right quick. All right. So again, key is making sure you got everything defined and paired up. It doesn't matter who you call 1 or 2. If I call this K2, I would call this T2. That means this would be K1. and this would be T1. Okay, so I want to plug everything in the equation and solve for it. So it'd be the natural log of K2, so 3.36 times 10 to the fourth, divided by K1, and K1 is 7.69 is equal to E sub A, divided by R, 8.314 joules per mole degree Kelvin. And it doesn't matter what the units of K are, because whatever they are, they're canceling out. So they're inverse moles, inverse seconds. So when you know both of them, they're gone anyway. All right, so now I just got to make sure that I get my temperatures right. So T1 was first, so inverse of T1 less the inverse of T2, so 344. Okay, so the way I would choose to approach this problem is everything on the left is known. So I'll just plug the numbers in. So the ratio is 4,369. And then significant 3, I take the natural log of that, and I find that it's 8.382. Okay, so I take the R, this, and multiply it over the other side, the value for R. And then I would start working on the rest of it. So I'm going to find out what's inside of the parentheses. Store that value. So 219 inverse less 344 inverse equals. So the difference in those is 1.659 times 10 to the minus third. So that's on the top. I'm going to divide it down to the bottom. So 1.659 times 10 to the minus third. So that should give me my activation energy. This was in units of inverse Kelvin. This was on the bottom, so the Kelvin were up here. The Kelvin cancels out. This is going to be units of joules per mole. So divided by 8.4. And I got basically 42,000. Yep. Joules per mole. That matches an answer. Yeah, answer is choice B. Okay. Most of you were there. Any question on what I did on the math? Go on with that.
I have a question.
Yep.
So I did it the other way around though. Like I did the 3.36 as K1.
Yep.
And I had it like this. At least.
Well, it would be if you the key thing. Did you swap these two around?
No, they're in the right order.
Okay,
I just
so
didn't get the right. I don't know. I got like 50 now.
yeah, let me go back and see if I can.
Wait. Pick it up. So this. Times is 2 by that.
All right, so this should have been just simply a negative 8.38. Did you get that? So if you had these switched over, this just becomes a negative 8.38. Did you have that value?
That's what I got it.
Okay. That was a negative 8.38, this number simply becomes a negative when you switch those around, and the negative and negative cancel out. It's the same thing. But what I suspect is that if you got the 8.38, that means you use natural log, not LOG. That's a common mistake we do. We use that one when really we need this one LN. It's just a multiply and divide problem then. You got the 8.38. So when you subtracted the inverse ratios here, did you get a negative 1.65 times 10 to the minus third?
Yes.
You did? Okay, so that just would go down here at the bottom. That's a negative. This is a negative.
I didn't get the 8. Mine says like 10.038.
For this number?
Yeah.
Okay, if you took the, that's where maybe you and your calculator have got to become more buddies. If you took the natural log of 7.69 divided by 3.36 times 10 to the fourth, that should be a negative 8.382. This number.
Parentheses the 3.36 times 10 to the 4th. So you put double parentheses, but you know.
Yeah. Well, yeah. Some calculators where you have to do that, that may be what's causing the problem. My calculator lets me hit the double E button, and I don't have to put a parentheses. So on my calculator, I just write in 3.36, hit the double E button, and put 4.
Close it. I had to use another parentheses.
Yeah. So that's the reason I like my old ancient calculator, because you don't have to use any parentheses. Okay. All right. We got a few minutes, so let's keep rolling. So the last topic in the chapter we're going to look at is looking at catalysts. So what catalysts do is they affect the reaction and influence the rates, and they're not consumed. What they do is they give an alternative mechanism for the reaction to occur, and it has a lower activation energy when the catalyst is involved. What happens is a catalyst is involved with the reaction in one of the early mechanism states, and then it is made available in the later state where it's released. If we look at the example of the ozone we talked about earlier, so ozone plus oxygen to yield O2. That's a very slow reaction. But in the presence of molecular chlorine or atomic chlorine, that reaction forms this intermediate very fast, and then this intermediate reacts with molecular oxygen, and it forms O2 gas. It releases this product back off, which is what we need as a reactant. So it's just constantly being recycled in the system. So the concentration of the monoatomic chlorine never disappears. With the catalyst, this reaction occurs very, very rapidly in the system, so in the presence of the chlorine. Now, when we look at catalysts, the catalyst can be in a couple of different states. So they all accomplish the same thing. They're giving a different pathway to allow a lower activation energy. If it's a homogeneous or heterogeneous catalyst, that means that it's in the same phase as whatever the reactant particles are. So an example is a catalytic converter on a car. It is a reaction where the catalytic converter is a solid. The gases that are coming by it or the things are in the gas state. So that's in separate phases. That's a common, the catalytic converter is one of the most common catalysts that we use in everyday life. So that's an example of a heterogeneous system. So that's I got the wording switched. So homo means one phase, hetero means two. So this is the homogeneous. So homogeneous catalyst is in the same phase as the reactant particles. Heterogeneous is where they're in different phases. So a catalytic converter is a heterogeneous reactor. Okay, so they still do the same thing. They change the orientation in some way and allow a lower activation energy to be created. So on the example, what's the purpose of it on a car? One of the problems that we had in the 1970s with the automotive boom that happened in the 60s and 70s is that we had a terrible problem in the United States with smog. And I had an uncle that died I lived in Los Angeles, and first trip I went to Los Angeles at the age of 5 or 6, and we drove up there. I remember we went over the mountains and we started going down the valley into Los Angeles, and it's this brownish red haze. I mean, it looks like a cloud on top of the city. It's terribly thick. And it was from the smog that occurs. When a car reaction occurs, when we think of a combustion that occurs in a car, what's driving the car is the fuel reacts with the oxygen in the air, and it produces CO2 and water. And CO2 and water, well, maybe CO2 is bad and water is good for us. So we think that's the primary reaction that's occurring. But the secondary reactions is that the nitrogen that's in this cylinder, this going up and down, this reaction is occurring at a couple of thousand degrees. There's a lot of side reactions that occur. Number one, not all of the carbon materials are completely consumed. Not all of it breaks down into CO2 and water. There's some carbon monoxide that's produced there. And there's a variety of compounds that we call NOx's. They're the bad guys. Okay, so it's a variety of different combinations of oxygen and nitrogen coming together. Those things come together and make the major pollutants of what we call smog. To the point that in the 1970s, if you had COPD, okay, so you had a decreased lung capacity, if you went outside during the day, your chances of being found dead on the sidewalk were extremely high. Okay, because the air quality was so low at that point. So the government realized that, well, we can make this catalyst that has a ceramic material that's got a metal impregnated in the surface, and the metal is most commonly a combination of palladium and platinum. It will take these compounds and break them down into their more stable states. So all of the NOx's get converted into N2 and O2. The CO gets converted from the more deadly carbon monoxide to carbon dioxide, which is not as bad for us. We breathe that out with every breath. And then we kick out water. So it's a much safer form. Now you go to LA, no smog over the city. Okay? But you want to see the smog, we don't have to drive as far. We want to see the smog, we just got to go to Dallas. Okay? Because the state of Texas said drive anything, basically. So in Oklahoma and Texas, we used to have, every year you had to take your car and you have to have an inspection done. So California still does it to the point when you come off of an on-ramp or onto an on-ramp, there's a device that takes a picture of your tag, and it's got a laser device that measures the output of these gases to a very precise level. If your car's not tuned up right, if it's producing bad gases in the environment, they send you a warning in the mail, and you have 30 days to get it fixed. Otherwise, they send you, they'll pull the car off the road. In Texas, in Oklahoma, we said, drive whatever you want. We don't care. And that's what we do. We don't do inspection stickers anymore. Used to, when I lived in St. Louis before we came here in the 1990s, they literally, you drove your car into the gas station, they put a probe up the tailpipe that measured these gases, and once a year you had to get that checked in order to get an inspection sticker. There's so many cars in Oklahoma and Texas that are running now. You get behind them in a stoplight and your eyes start watering, okay, because they're so out of tune the way they're running. They don't have catalytic converters. They cut them off because they are very expensive to replace, but they're terrible for the environment and they're terrible for what you breathe in. Okay, we'll continue this up. We only like a few slides over Catalyst, about 10, so we'll finish that on Wednesday at the start of class. I don't even know if we have any clicker or master chemistry questions over there. Okay, see you tomorrow.